We start off with our first class of the chapter mathematical reasoning, and as you can see that this is a collaborative class. We have our Abhishek Paul sir giving us few ideas, or rather he is describing or explaining us the whole chapter, the whole topic for today, and I will be solving few problems after he has completed his explanation. Now, today we are going to learn few things. So, the first thing is what is a proposition or a statement. Then we will be learning what we mean by compound propositions. Then, what are logical connectives. Then, truth tables. Now truth tables are something which most of us are acquainted with, but still we will be learning it in a new way. And then we are going to learn what we mean by a tautology and a contradiction. Fine. So let us take you over to Paul sir. He will be explaining the chapter now, and once he is done we will come back and we will be solving few problems. So over to Paul sir.
Hello and welcome to Classroom Simplified. So in this video, we are going to understand all the details related to the chapter named Propositional Logic. So this term logic, it's a very common term. Even you can relate this term with various examples in real life scenario. First of all, it's a very important and it provides us a way to support our claims to truth. We can define logic in many ways. We may say that logic is all about arguments, or in a simple way, it is a formal method for reasoning. And this propositional logic represents logic through propositions and connectives. These are logical connectives. We will be learning all about this definitions and the concepts. What is proposition, what are these logical connectives, one by one. So coming to this proposition is a declarative statement. These are simple sentences which can be said to be either true or false, but not both. Okay, or it should not have any other value also. So these are all declarative statements and which should have either true or false as its value. Okay, now talking about the examples below, it is cloudy. So this can be either true or false. If it is cloudy, it can be termed as yes, this statement is true. So it is a propositional statement, right? So it is a proposition. Now next one, you will like this video. Suppose if you don't like this video, then it will be false. And if you like this video, then it will be a true. This statement is also giving either true or false as its result, right? So this is also a proposition. But in the next part, in this third example, how are you, it's not a proposition. Why? It's not giving any true or false kind of result, right? So this is not a proposition. Or what did you eat, this is also not a proposition, as it is not giving any either of this true or false kind of result. So this was the definition and few examples of proposition. Now we will be looking into the details of it. So here it is given every rectangle is a square, and lowercase p is denoting this proposition, right? So you can term with this lowercase alphabets for any representing any proposition, like the lowercase q can is termed like 16 is divisible by 2. So p and q are therefore two propositions which are having certain truth values. And what are these truth values? Suppose the statement which this p is representing, that is every rectangle is a square, is it's actually false, right? Because every rectangle is not a square, so it is representing false as its value. So this p value, the truth value of this p, will be termed as 0. Similarly, if I say that 16 is divisible by 2, so this statement is of course true. Why? Because 16 is divisible by 2, and truth value of q will be termed as 1. So any value which is true, that can be termed as 1. So any value which is false, that can be termed as 0 for that respective propositional variable. Okay, so let us see more. So now talking about this compound proposition. This compound proposition is one with two or more simple propositions as parts, or what we will call components. Okay, so here an operator or connective, it can be more than one also, I can join simple propositions in compound okay, and joins compounds into larger compounds. So compound proposition can be formed using this connective and combining various simple propositions together, and therefore forming this compound proposition. So let's look into the details of this compound proposition with various examples given below. So we can see the first example, it is cloudy and it is raining. So here two simple propositions are joined using this connective, and this and is also known as conjunction, and which is used to combine these two simple proposition to form a compound proposition. In the next example, take it or leave it. You can see two simple propositions are joined using this connective or. This or is also termed as disjunction in this part, and we will be understanding all these details of this conjunction disjunction in the next part. Okay, coming to the third part, you can see that if you work hard then you will pass. So this is also a compound proposition where if then has been used, connective if then has been used, that is conditional, to work upon this two simple proposition, that is you work hard or you will pass. So those two simple propositions has been joined together to form this compound proposition. Another one, the last example, is if and only if then this kind of connective has been used to combine this two simple proposition to form a compound proposition. So this was the part of compound proposition. So we will be learning about the details of this connectives and how we can form further more larger compound propositions that we will be looking at. So basically we will be using all these connectives like or, and, if then, if and only if then to form compound propositions. So they are also called the sentential connectives because they join sentences or what we are calling propositions or statements over here. So we have understood about how to form compound proposition with the help of these connectives. Now we will be looking in depth into this connectives. So these logical connectives are also termed as operators, and by the definition of these operators we know that operators works upon operands to give us some results. So here also these connectives will be working upon this simple proposition to form this compound proposition, and we have to get the output of this compound proposition or the truth values of this compound propositions. So let us see the first connective which is the negation. This negation is also termed as a not operator which works on single proposition only. Okay, it is also called unary connective sometimes, and we can say that if P is a proposition, if P denotes a proposition, then its negation will be written as this kind of symbol and then P, or it can be also written as P dash or sometime P bar. Okay, so let us follow this rule, negation of P. So basically it works on single proposition. That's why we have taken this input as P. So if we form the truth table, what is this truth table? Truth table basically brings a relation between the input and the output for that particular instance. Suppose at this moment the P value is 0, means it is false. So it will give the negation of that P value, that is 1. Similarly, if I write or take as input 1, that is true, then it will give as 0. So basically it is inversing the value. If it is 0, P value is 0, then the negation of P will be 1. If the P value is 1, then the negation of P value will be 0. So this way we can denote the output and input logic from this truth table, and we will be looking all the details of the truth table for each and every logical connectives. Now let us look into the details of this disjunction. This disjunction, or it is also termed as this or connective, and which works with more than one proposition. So if we take more than one, means two I am taking, suppose two proposition which is denoted by P and Q, then the disjunction will be termed as P or Q. In you can also write like this way, P plus Q. Okay, so these are the ways of writing this disjunction operator combined with two simple propositions. And then coming to the next part, we will be understanding about the truth table of disjunction. So here 4 instances or 4 rows I have written. Why? Because it follows the formula 2 to the power n. what is n? N is the number of variables possible. So it will be giving us 2 to the power n terms. Like if a compound has n distinct components, there will be 2 to the power n rows in its truth table. This is a this you have to keep in mind. Okay, so here it's actually two variables p and q, so I'll take 2 to the power 2, that is 4. So 4 rows, that is 0 0 0 1 1 0 and 1 1. Okay, so these are the combinations and the rows which we got, 4 rows, and for each and every row we have to see what the output will be. Now this disjunction says that it will be true, the result will be true whenever p is true or q is true or both are true. So where we can search for where p is true or q is true or both are true is in this second row, third row and fourth row. So we can term all these three as one or true. So why? Because it has been defined as this disjunction result will be true whenever p is true or q is true or both are true, but the rest will be false. Whenever we get p as 0 and q as 0, we will term the output as 0. So here is the result. So basically this was the details of this connective disjunction, which is also termed as OR operator, and we have understood about its definition and truth table, and examples which we have seen it earlier was that take it or leave it. So here take it and leave it has been joined together with this operator OR. So coming to the next conjunction part. So this conjunction, which is also termed as this AND connective, with the help of which we can form compound propositions where more than one proposition will be used. Like we have seen in this negation part, only one proposition was used, but in the disjunction and this conjunction, more than one proposition will be used. And suppose if I take p and q, which is denoting two different proposition, so we can write the conjunction between this p and q as p conjunction q. You can be also term it like p dot q. Okay, so this can be, this one or this one can be termed out of this conjunction. So if I take the truth table, firstly we need to define it, that what it says. So it says that whenever p and q both are true, then the output will be true. So where we can see that p and q both are true, this one and this one, so it will be termed as true. In all other cases it will be termed as false. So example also we have seen it before, that it is cloudy and it is raining. Here two simple propositions, like if I denote it is cloudy as p and it is raining as q, then AND operator has been used to form this compound proposition that it is cloudy and it is raining. So moving to the next connective, that is conditional, we will see in detail. So in this conditional, which you can see that it is also termed as implication, or it is written as if then, you can term this p implies q as if p then q. Okay, so two different propositions I have taken, p and q, which can be written as p implies q. You can also write like p single arrow and then q. So what it says basically, so here p, the first one which is at the left hand side, is known as antecedent, and which is at the right hand side, the proposition, will be termed as consequent. So later when we will see more examples, you will observe that this antecedent and the consequent both can be compound propositions, means combinations of more than one simple propositions can be combined together to form this antecedent, or combination can be formed to form this consequent. That we will see it later, but here let us work with more than one, because this conditional takes more than one proposition to work with. So p implies q, basically if we define it, p implies q will be false when p is true but q is false. So where p is true but q is false? Here. So this row, third row, will be termed as false, but in all other cases it will be termed as true. So we have seen about that example, that if you work hard then you will pass, right? We have seen it before, that compound statement, that if you work hard then you will pass. So here you can say that if you don't work hard you will not pass. Yes, that is true, that's why the first row is true. Second row says that if you don't work hard then you passed. So somehow he has managed to pass, like maybe he made a smart approach to the exam purpose, or he has gone through only the questions which came up in the previous year, or he has got some important questions and he has passed. So without doing hard work he has passed. So that may be possible. Why? Because the q, that is the goal, has been reached, that it has been passed, so we can term it as true. But here in the third row, you have worked hard but you have not passed, is not a valid one. So that's why it is giving us false result. But in the last case, if you have worked hard then you will pass, yes, it is giving us true result. So this is what about conditional or implication part. Now we will be looking into the biconditional one. So coming to this biconditional, it basically results in false when one of its component proposition is true and the other is false. So where we can see that one component is true but the other is false is in this second and third row. We can see that P is false but Q is true. Similarly, in the third row is having P as true but Q as false. So we can say that these two row are false, but others we can term it as true. Why? Because one example we have taken it, that if and only if you understand, then I will stop. Okay, so if and only if you understand, then only I will stop, it will satisfy. When this is true and this is true, yes. And if you have not understood, then I will not stop, yes. So I will continue, that is also true. But either or means one P is false but Q is true, or P is true Q is false, will not satisfy. Okay, so this was the part of the truth table and the definitions of different logical connectives, or we can also term this as operators. More details about a few other terminologies which are used in this proposition part. One is this tautology. So if any compound proposition you get and the result is acting like it is always true, then that compound proposition you can term it as tautology. Like P disjunction means P, or you can also term it like P plus P dash, right? So this one will always be true. Why? Because one value you are getting, the other will be the opposite of it, and you are doing simply or, right? That is that disjunction, and from disjunction it says that either one variable or the other variable be true or both be true, it will result in true. So here if P is false, you can see from the truth table, if P is false, then its negation part will be true, therefore it will result in true. If P is true, its negation part will be false, but it is, since it is or, therefore it will result in true. So both the cases, it will bring the output or truth table result as true. Therefore P or not P will be a tautology. It will be termed as a tautology. Coming to this next part, contradiction. So if any compound proposition is always false, this is just the opposite that to that tautology. And in case of tautology, we were getting the output always as 1, but in contradiction, we were getting as we are getting as 0, right? So example, P dot P dash. So why? Because this dot is representing the and operator, or this conjunction, which will be true only if both the cases are true. But here both the cases can't be true, because this P dash is the negation part of P. So here if I take P as 0, then P dash will be 1, and if I take P as 1, then P dash will be 0. Therefore it will result in what? Conjunction will result in 0, because 1 0 present, it will bring 0 in this conjunction part. Both need to be true, then only you will get true in this conjunction part. Okay, so contradiction is like compound proposition which results in always false, and tautology is a compound proposition which brings up always true result.
So thank you, Paul sir. That was a very wonderful session from you. Now let us move to examples. Obviously, now examples in computer and examples in mathematics will be a little bit different, because in mathematics we are more interested in taking up statements or propositions which are related to mathematics. So to begin with, let us have the first question, which is identify which of the following are statements or proposition. Now, as sir has explained, that proposition or statement means that it should be declarative in nature. That is, it must have two answers to it, either yes or no, or true or false. So let us have the set of questions that we have. Now, to begin with, we have a very racist example, that is, Krishna is black. Now, what can be the answer to this question? Krishna is black. Now, obviously, you can have the answer yes, he is black, or you can have the answer no, he is not. So, whenever you are having an answer to any sentence in the form of yes or no, true or false, then it is considered to be a statement or a proposition. So definitely in case of the first one, we can have the answer yes or no. So therefore it is a statement or proposition. How black is Krishna? Second one. That is again another very racist question to ask, but is it having an answer yes or no, or true or false? Obviously it is a question. Now generally questions don't this question don't have an answer yes or no, and therefore it is not a proposition. Fine. Next, 2 plus 5 is less than 11. So 2 plus 5 is basically 7. 7 is less than 11. So it is definitely asking you a question, yes or no. That is true or false. Now obviously 7 is less than 11. The answer is yes. Means I can answer this sentence by saying yes or no. So therefore this is again a proposition. Then x square plus 5x plus 6 is equals to 0. Now x square plus 5x plus 6 equals to 0 need not be always so, because for different values of x you get different values. So x square plus 5x plus 6 is not always 0. So the answer to this question can be yes, it can be no, it can be maybe, because it can have any kind of answer, not always a yes or no answer. So therefore this is not a proposition. Then do your homework. Do your homework. You are ordering someone or you are requesting someone. So this kind of imperative statement where you are ordering, requesting, instructing, they can't be a proposition. Why? Because they don't have an answer yes or no. So therefore this is not a proposition. Fine. We are done with our first example. Now let us move to the second one. Example number 2. State the truth value of the following. State the truth value of the following means you have to say if the statement or the proposition is true or not. Let us take the examples. So here we have all the examples. Now let us see if they are true or not. There are finite number of rational numbers. Now, is it true? Obviously not, because there can be there are infinitely many rational numbers. So therefore this statement is false. 0 is a complex number. Is it true? Yes, it is obviously true, because 0 is basically a real number, so it is definitely a complex number as well. 2 plus 5 less than 11. Yes, it is true. It is definitely true. Then pigs fly. Well, in our day-to-day life, in our real world, it is something that really doesn't happen. But if you are in Hogwarts, you have something called a gargoyle, and they are like flying pigs only. So that is true there in that world, but in our real world it really doesn't happen. So let me know if you see one, but I haven't seen. So definitely it is a false statement. Fine. Then the next one. There are 12 days in a week. Obviously not on Earth. It can be on any other planet, but definitely not on Earth. So as we are on Earth, so for us it is false. Fine. So that is how you state the truth values of a proposition. Fine. Now let us move to example number 3. Number 3, we have write the negation of the following statements. Now, first let us take a statement and then let us write its negation. Negation means it is more like what you have done in your junior classes, writing affirmative and negative sentences. So 17 is a prime number. So this is your statement given. So you want to negate it. Negate it means you are trying to write the opposite of it. So 17 is a prime number, so obviously its opposite will be 17 is not a prime number. Now you would like to write 17 is a composite number. Well, yes, you can write that as well, but writing 17 is not a prime number means using that word not is very important here. So writing it as 17 is not a prime number it makes more sense. Let us take the second one. 2 plus 7 is equal to 6. Now obviously it really doesn't need to have a meaning, but it is a statement for sure. Now its negation will be pretty much 2 plus 7 not equals to 6. Equal to, not equal to. So negation of equal to is not equal to. Next, every natural number is an integer. So your negation will be every natural number is not an integer, or you can write not every natural number is an integer. So you can means taking care of the grammar part, the English part, which is completely up to you. Now this is definitely not an English class, so you can be a little bit liberal with what you write, but definitely it should be grammatically correct. Next, all men are mortal. Well, I hope they were. Fourth one, all men are mortal. Now, this one is a very open statement, and this can have different kind of negation depending on which particular word you are emphasizing on. Now, the very obvious negation is not all men are mortal. This is a very obvious negation. All men are mortal, not all men are mortal. Now, there is another fancy way of writing it. Now, this will be straight out of your English grammar. You can write, there exists at least one man who is not mortal. Now, that also makes the same sense. If you are saying that all men are mortal, and if you want to negate this statement, then definitely there must exist one man who is not mortal. That just makes sense. So this is how you write the negation of statement, right? Let us move to number 4. Find the component statements of the following compound statements. Clearly mention the connecting words. So this is basically again from your grammar classes. If you remember, you did that simple sentence, compound sentence, and complex sentences. So here we are working with the same kind of a situation, but we are dealing in the perspective of propositional logic or mathematical reasoning. So let us take the first question, that is, Jack and Jill went up the hill. Now you have to find out what are the individual statements that you have, or the component statements. Now obviously Jack and Jill went up the hill. So Jack went up the hill as well as Jill also went up the hill. So definitely the component statements will be Jack went up the hill and Jill went up the hill. So these are the two component statements, and pretty obviously the connecting word here is and, which in English we call as conjunction as well. In case of proposition also we call this as conjunction. Now next we have all integers are positive or negative. So as you can see, there are two component statements. The first one being all integers are positive, the second one being all integers are negative, and here the connecting word is or. Now or, according to propositional logic, it is also called disjunction, but if you just go by English, it is still a conjunction. Then the third one, let us take a third example. 36 is a multiple of 2, 6 and 8. Now as you can see, there are three statements involved. So the three statements are 36 is a multiple of 2, 36 is a multiple of 6 and 36 is a multiple of 8. So there are three statements involved and it is connected by the connecting word, that is and. Fine. Let us move to question number 5. Question number 5. For any statements P and Q, construct the truth table for the following compound statements. Now, the compound statement given here is negation of P or Q. Now, we already know, we have seen how to construct a truth table. Some of you who had computer, you already know it from the beginning as well. Now, in case of mathematics, as Paul sir have shown using 0 and 1, that is exactly how it is done in case of computer. But in case of mathematics here, we are going to make use of T and F. T means true, F means false. So it is basically a replacement of 0 and 1. 0 is basically false and 1 is basically true. So therefore we are just changing the nomenclature using a different symbol. Instead of 0 and 1, we are using T and F. So rest of the whole idea remains the same. So let us first do what? Let us first write all the possible combination of the inputs. Now P and Q are the inputs. So therefore let us see what are the different possible combination P and Q can have. So P can be true, Q can be true, P can be true, Q can be false, P can be false, Q can be true, and then both can be false. So now we have to construct the table. So negation of P means it is giving us the opposite value of what P is having. So P is true in this case, so therefore this is going to be false. Then this is going to be false as well. This is going to be true. This is going to be true. Then not P or Q. So we know in case of disjunction or, if one of the value is true, then the whole value becomes true. So therefore this is true. This is true. This is also true. This is true. I'm sorry. In case of disjunction, we know that if one of the value is true, then the whole value is true. So therefore, in the first case, one of the value is true, so it is true. Here both the values are false, so it is false. Here both the values are true, so definitely true. And here also one of the value is true, so it is true. Right? And then again, we have negation of that. So whatever you have done here, we have to just reverse it down. So it will be false, it will be true, it will be false, and it will be false once again. So now if I just remove all these and just type it down everything, so this is what you get. That is, this is our truth table. Next, Number 6, for any statements P and Q, show that P and Q and negation of P is a contradiction. Contradiction means we have already seen that the outcome will be always false. So any statement is called a contradiction if it is always false, doesn't matter what. So therefore, again we will be doing the same thing. We will be constructing the truth table here, and just go through it, just do the calculations all by yourself, and you'll see that you get all the final values, all the values as false. So therefore, doesn't matter whatever the value of P and Q is, this particular statement, this particular compound statement will always have the logical values as false always. So therefore, it is a contradiction. Fine. So that's it. That is our first class. Hope you have enjoyed. And as always, if you have any doubt, please get it clarified. Thank you.